Dr. Ott. Okay, can everybody see me?
Yes.
Okay, wonderful. Okay, I had to go to the browser to get things set up here. Okay, I guess we have 16. Oh, we have 19 participants. Dr. Ott, most of the people are virtual today. Okay, so they'll be asking questions over that. Okay, now what we're going to do is continue where I left off, and I want you to keep in mind that these are models, and the models fit with real life, and the real life was proved using mathematical equations as well as experimental stuff. So the models really help introductory students understand what's going on with it. So basically, what we're going to do now is get, oops, wrong one. Go back here. Okay, this is where we stopped here with this, and I didn't, and it, Dr. Ott, this slide is animated, so it's got this on it while I do that. This is previous day. So. Okay, I'm going to share the screen with everybody now, so we can get going. Okay, can everybody see me? Can everybody see the screen?
Yes.
Okay, wonderful. Okay, let's start. Basically, these are the notes I did yesterday. And so what I'm going to do now is essentially look at the different examples here. When the difference is zero between the electronegativity, you have what's called a covalent bond. And an example is here, there with the chlorine, okay? And this chlorine here is a covalent. That's why the double dot has been switched to a line there. So essentially that's an example, because on the electronegativity chart, chlorine is over to the right, but they're the same number. I believe it's 3.5. So 3.5 minus 3.5 is 0. So that's just one example of that. When it's greater than 2, we have cesium fluoride. So here, this is 0.7 and this is 4.0. So the difference is 3.3, and that is considered ionic, okay?
Dr.
When you look at something like hydrochloric acid, where you have 2.1 for the number for hydrogen and 3.5, it is here, the difference is 1.4, so that's considered polar covalent. Okay?
Dr. Douglas?
Yes.
Will we get the electronegativity chart on the test, or do we need to put that on our flashcard?
If you wish to put it on your flashcard, you can, but otherwise, I prefer you just to see the trends on the periodic table I give you. As you go to the right, it's more electronegative. As you go down, it's less. Okay?
I mean, I understand that part, but with the specific numbers, how will we know if it's...
You're not going to need them. You're not going to need them. And I'll give some examples in the next slide regarding being able to look at them and see, is it covalent, is it ionic, or is it polar? Okay, and then I'll give you little examples. Okay, so basically, let's just continue there. You got polar covalent, and I'm going to erase what's on the slide here, so you can see more of what's there, and then back to the pen. And this is considered polar covalent, and electronegativity goes like this. So if you remember the periodic table here, I believe it was Brandon, you asked the question. The periodic table, you just look at it like this, and the standard periodic table I give you, as you go across to the right, fluorine is over here and chlorine. So what are you going to know about the electronegativity there for these on this side? It's going to be higher, correct?
Yes.
Okay, and down here will be low, and cesium and francium are 0.7. So again, you don't have to memorize the numbers, just understand the concept of what you're doing as you go across a periodic table. So once you get the hang of practicing it, you'll just be able to look at that thing and say, okay, that's in the right corner, that's higher electronegativity. And if you remember what electronegativity is, it's the tendency of the electrons to be drawn to itself in bonding, okay? So it's almost like one thing is grabbing electrons more for itself and not as willing to share. So covalent, they share electrons. Polar covalent, partial transfer of electrons because they're dragged closer. And then ionic is a full transfer of them. So basically, there's a whole lot of differences there, differences between them. And if you look down at the bottom here, chlorine as a molecule is 0. And then you got IBr and HI and other things, and then all the way up to lithium fluoride and cesium fluoride and other things. They're up here regarding percent ionic character. And that has to do also with solubility in water. Is the more ionic it is, the easier it is to solubilize, okay? Because the water molecules break them apart. Now let's do a little skill exercise here. And just look at your periodic table when we do that. The bond in cesium chloride, and I'm going to draw on this first before I show their art. What is that? That's ionic. Why? Yeah, metal to non-metal. And where are they on the electronegativity thing? Yeah, opposite sides. Very good. Okay. So H2S, let's draw that first. So you put this in here with the S, and then here, the H over here, and then the H over here. Is that going to be polar covalent or ionic or covalent? Well, if you look at the numbers, and you'll be doing this when you do your homework, look at the numbers, you'll see that the sulfur is more electronegative than the hydrogen, and so they go into the center there, so that's polar covalent, okay? And then, for example, the nitrogen bond in this structure, oops, you have that like that, and then you have an H over here, and an H over here, and then an H over here, and an H over here. Basically, you end up an electron pair there as well as there. This one is 0. The difference between the nitrogens are 0. So what is that going to be between those nitrogens? Covalent, yeah, okay. Because they're equally shared. So if you were doing dots, you put them right in the middle like that. Okay, so if you look at the different places on here, there cesium is 0.7. And let me erase the stuff on the slide, go with their art now. Yes. What? Oh, okay, the H2S, if you got, I got to draw it on here again. Well, here with the sulfur, if you look at the chart like this is the sulfur, right? That's the sulfur, right? And you go back and look at the chart here. See the chart? Where's sulfur on this? It's 2.5, right? And hydrogen is 2.1. So the difference there is 0.4, right? Okay, so that is slightly polar covalent. Well, no, just the general trends because the sulfur is on the right, so it's more electronegative, and the hydrogen's on the left, so it's less. Okay, so you can still use the chart. You still have that relationship. But I don't like their hard and fast rule saying it's 0.4 because I want as being covalent because I want you to understand it's still polar. It's just not as polar as a water molecule is because essentially sulfur is right below this and you have oxygen with a hydrogen there, and that is more polar than H2S, but it's still it is still polar covalent, but it just happens to be more polar and you'll get into that later when you talk about polarity with hydrogen sulfide versus water, polar solvents and organic and other things like that. So basically, the nature of polarity has to do with the differences in electronegativity. If it's 0, there is no polar aspect. But if it's 0.4, there's still an arrow pointed in the direction of the sulfur. Okay, so basically, go back to the slide again. Did that answer your question? Okay, so if you got these with this, and if I don't remember the numbers, so I'm not expecting you to, this is 2.5 and this is 2.1. So where does the vector point? Nick, where does the vector point there? Towards where? Which atom is more electronegative?
Towards sulfur.
Yes, towards sulfur. So you draw the arrow in like that with the plus end at that end as well as at that end there, but it's not a linear molecule because you still have those electron pairs here and here.
You want us to put plus signs to say.
Dr. Douglas, what were you talking about with the plus and minus ends and a vector?
Well, the vector is represented in mathematics like that, with a plus sort of at this end, and this would be more the negative, and this is the positive one.
So
Okay.
what side of what element is which?
Well, the sulfur is 2.5, right? The hydrogen is 2.1. So the arrow would be directed towards the 2.5 because this is more negative than that. So if you were to draw it, the structure like this, these electron pairs would be slightly closer to the hydrogen than slightly closer to the sulfur than they would be right in the middle for something 0. If you have a chlorine like this and a chlorine, this electron pair would be right in the middle. The arrow doesn't really represent it that way, but these are in the middle because they're equally strong pulling in both directions. So they'll be right in the middle. Whereas this will be slightly closer to the center. But if you got something very electronegative like hydrogen fluoride or cesium fluoride, it's all directed towards this. So this has essentially become ionic. And so now this is -1 and this is +1. The cesium has essentially given up that extra electron. So that's why it's called ionic. And the difference there is 3.3. But that just happens to be a number that they calculated experimentally. Okay?
Dr. Douglas.
Yes.
Okay, so you said those numbers you don't expect us to memorize. So are you going to give us a chart with them, or in the questions are you just going to say it?
No, basically, you're going to have this periodic table, right? And I want you to remember the trend. It goes, this is more electronegative going to the right, less
Yes.
going down. Okay? That's
Yeah.
enough.
Okay.
That's enough to answer any of those kind of questions, particularly those of you, because getting into later, you get into electrochemistry in grad school or in physical chemistry. Yes, the numbers are going to be more important, but at general chemistry level, don't worry about it. Okay?
Thank you.
So basically here, I'm going to erase what's on the slide now. Is it okay with you, everybody, to erase what's on the slide? Okay, good. So. Okay, so now we'll use their pictures again. I gotta make a pen so I could draw on it. But basically the difference is there is 2, 0.4, and that is polar covalent. But if you looked at that chart with the numbers on it, it would say covalent, but I only consider covalent as being if you have 2 carbons, like in a hydrocarbon, if you have 2 carbons like this together, this would be pure covalent bond. And those are inorganic compounds. So that's considered a covalent compound when you got hydrocarbons. And then with nitrogen here, with this, 3 minus 3 is 0. So that would be covalent. Okay, now writing Lewis dot structures. This is where the chapter ends, and it really is pretty good. And before I get into the rules, I'm going to use this blank to do it ourselves, okay? So if you remember our little periodic table we made yesterday, with the little things like this, and you have X's above it. And I do want you to draw one again for yourself so you can do it for yourself, and then put 3 around it like this. And what we're going to do is construct little things as we go across. Okay, so essentially you have going all the way over to 7 and then 8 on the right. Okay, so I have a set of rules that's kind of pretty helpful. Okay, the big atom goes in the middle. Goes in the middle. So, and the others orient around it. Others orient around it. Now, what is more compact? If you've got 5 elements, like just look at this example, CH4. Okay, how many atoms are in that molecule? 5, right? What is going to be more stable? A chain with 5 links that goes out like this, and they're relatively weak, and so you can shake it and they'll fall apart, or a ball where everything's together. A ball, okay? So chemicals work the same way. So this will want to be efficient and be around the carbon. So you start with the carbon, okay? So basically you start with the Lewis dot structure for the carbon. You see where it is on the periodic table? You put 4 in it. How many hydrogens are there? 4. So basically you put them around at each place. Okay? And notice there's an electron pair at each place. What does that do? Forms a bond. Very good. You now have the Lewis dot structure for methane. Easy, right? Yes. Other orient around it. That's the example that I had with the see the thing. Because some students make the mistake of doing this. H, 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 and it happens even in Kazakhstan where people line them all up like that. Okay? Obviously it's wrong because the hydrogen can only bond in one place, but they broke the rules there, and so they made it all floppy. Well, that's wrong. So I'm asking you to kind of think differently about it. See it as a ball. Yeah.
You're gonna want us to do like the hydrogen's gonna be more of a plus on those.
Well, then you get to the electronegativity thing, because if you look at the electronegativity chart, this would be 2.1, and carbon, I believe, is 2.5 or 2.7 or something, but it's still polar. The vectors are directed in, but they're all around it. So that's considered a non-polar molecule, because in vector algebra, all those vectors cancel out. They're in a 3-dimensional thing and they all cancel out. And that's covered in college algebra as well as vector algebra, where you've got, if you have 2 vectors that go in an equal thing and they are essentially going in at equal strength on either side, those cancel out just mathematically, because you can move the vectors and see that they go back to the same place. Okay, that's vector algebra. But that works here too. And so the methane is considered a non-polar molecule. But I digress, because I appreciate you thinking ahead here. What about this? This is another electron dot structure, but very similar to that. But is that polar or not? That's polar, right?
Yeah.
Because this is different. But also it has these electron pairs on there too, which are more minus. So this side will be more, this side will be more minus, this side will be more plus. So that's why methanol can dissolve some salts. It's not as good as water, but it still is, okay? But that's a little bit off. So what I'm gonna do now is erase.
Dr. Douglas,
Yes,
is the big atom based on the atomic radius?
yep,
Okay.
yeah, and hydrogen is very, very small. And again, you're thinking ahead, which is great, fabulous. And you're thinking like a chemist, that's wonderful. So just keep it up, okay? Okay, now the 4th rule is, if you run out of things, and let's just do another example, and I'm gonna switch back to the pen again. We'll use this example. CH3OH. Okay? And again, you don't line them up. What's going to go in the middle? And if you look at the periodic table, which is the most holes on it? Which has the most holes on it? The oxygen that has 6 around it, the carbon has 4. So which one has more things it could bond with? The oxygen has
Carbon.
6 because oxygen
The
looks like
carbon.
this. Yes, so you had a comment?
I was saying, like, wouldn't it, I don't know. I was trying to, like, answer.
Okay, what was your answer?
Wasn't it the carbon because it has
Yeah,
less? Wouldn't it
yeah,
go
very
to
good. So you got 4 on it. So you start with that one. Okay, you start with the carbon
Wait, why would you not start with the oxygen?
because it has 6. It looks like this. How many holes does it have? How many places to form a bond?
2.
Just 2. Well, you start with whatever has more holes in it. It's like making a charm bracelet or something that you have 4 places you could put it, the other charm, versus 2. Like if you just have 2 places, that's like a chain extender. If you have just 4, you can have it be in the center. So in this case, you're putting it in the center, okay? So what's the next one that has 2 around it? Well, you put the oxygen next to it, like this, and spread them out. You form a bond there. Now, how many holes do you have now that the hydrogens can go into? 4. And then you play, and notice you have 4 hydrogens left. So one will go here, one will go here, one will go here, and one will go there. You're done. That's the Lewis dot structure for that. Okay? You see that? So again, the book unfortunately teaches it using counting up the electrons and all sorts of things. And I understand that method. If you want to use the book method for doing it, if it's easier for you to do that, great. But I don't teach it to my students because this way works better and it fits better with organic chemistry. Because as Dr. Ott would tell you, do you ever count, when you're asking the people who do Lewis dot, do they ever count the electrons or are they just supposed to draw the structure?
It's a mixture of both because I've seen people draw structures and they're not keeping track of their electrons, and it's something that looks reasonable, but it doesn't add up to valences.
Yeah, okay, so basically there's a combination of both. As you get to the higher levels, there's value in doing it both ways. But when you're learning it this way, then you'll understand that it's better to just draw the structures and keep it simple. Otherwise, you bring the numbers in, then you get lost and you add and subtract the numbers wrong and you miss the point about what you're trying to do regarding putting bonds together. And I grew up with Tinker Toys, so I put things together, okay? Erector set or Tinker Toys. So that's my background. But I'm gonna erase some of this slide again and then go to the next one here and give another example. Okay, so now let's do this one for, oops. So we go to this one, 4, and you have CH2O. Okay, what's going to go in the middle? The carbon. So you put 4 around it, 1, 2, 3, 4. What would go next to it? The oxygen, because you have 6. 1, 2, 3, 4, 5, 6. And then you form a bond here. Now, how many holes are left? And I'm going to erase part of the slide here. And put the pen back on. Okay, here, you've got 1 bond here. So how many holes are left? How many plain single dots are left? No, how many holes are left? Not atoms, how many holes are left? Huh? Well, you have 1 here on the oxygen, right? And then you have 3 on the carbon, so you have 4 of them, correct? Well, there is 1 on the oxygen. I'm sorry, I messed that up part again. Let me get rid of this one, see? Okay, so here you got 1 here like that, right? Huh? Yeah, and that's the next step. because you have 4 places, but you only have 2 hydrogens left, right? You've got to form another bond somewhere else. So you take this one here and this one here, and you form a double bond. So now how many holes are left? 2. So where do the hydrogens go? Yes, very good. So you put a oops. Sorry. You put 1 hydrogen here. You put 1 hydrogen here to do that, and 1 hydrogen there to do that. Okay? And then it reorients and looks like this. And then you put the electron pair there and there, and that's the end of the structure. Does everybody see that? Do you see that? Okay? Now, does that look linear to you? No, you can make a triangle with this, and it's flat. It's kind of like stuck flat with 2 wings out like this and the other in the middle with a double bond. This is called trigonal planar. And we'll talk about that more next chapter, but that's the geometric structure. That's called trigonal planar. Okay? Yes. That's a double bond covalent, yes. Okay, and you have 2 bonds, and we're going to talk about the nature of hybrid orbitals and everything in the next chapter. But right now, we're just doing Lewis dot structures. Okay, so now let's go to the next thing. I'm going to erase part of his slide again. Yes?
So this type, the CH2O, that wouldn't be on the test ever.
It might be. Why not? Okay, and that's why I'm giving you a whole bunch of practice problems to work on over the weekend. Okay, and so that's I've had every student learn to do this, but again, you practice by going through the same steps I was with you, and you can look at this multiple times, this video. Yeah.
So we will not need to know the like the shape of the structures for like the methane and the CH3O8.
Well, that's called tetrahedral, but we're going to talk about that in the next chapter. Not right now, no. And I'm not even going to mention linear or trigonal planar. I'm just introducing you to that topic because many of you are already thinking ahead. And I want you to see it as geometric, as 3-dimensional objects in space. Okay, but tetrahedral, octahedral, and the other things, they're more complicated. That's more related to hybrid orbitals, okay? Okay, so basically I'm going to mess up the slide more. I'm going to use the eraser on it and delete the last, delete what I just put on here, but you can look at it again on the video. I'm going to go back to the pointer now. So now let's do another one, and this would be number 5, CO2. Okay, what would go in the middle? What? The carbon, good. 1, 2, 3, 4. Where do the oxygens go? On either side, good. That's the logical part. So essentially you got the oxygens on either side. And you put 6 around them. You form 1 bond here first and then another bond there. Now, how many electron pairs do you have available for bonding? Electrons do you have available for bonding? Count them. Yeah, 2 more with carbon and 2 with oxygen, 1 with each. So then this one you can take and form a double bond here. This one you can take and form a double bond here. So the result is, it looks like this. The electron pair there and there, electron pair there and there. So what structure is that? Linear, very good.
I thought a triple bond was linear.
What? It is. Brendan, very good. You're thinking ahead. That's number 6. Okay.
Wait.
Brandon,
So-
you're thinking ahead. That's number 6. I'm about to get to number 6. Good.
Well, so a double bond and a triple bond is linear?
Yeah, and I'll show you in number 6. But I want you to see now that this with carbon dioxide, that's things too. Yes.
Dr. Douglas.
Yes, the video person can ask first. Yes.
So the element with the most holes will always go in the middle.
Correct. Because you want building blocks on to go around the one on the center.
Okay.
Okay. So yes, Nick.
So every Lewis dot structure that we do with the molecules, each elemental atom will have a full valence.
Yeah, they will all want to obey the octet rule. That's the thing, key thing. Count the number of electrons around the oxygen. How many are there?
Well, if you include the bonds, it'd be 8.
Yeah, and as well as the carbon has 8 around it. So they're all happy. They're all pretending to be neon by sharing. Okay? So now, because this slide has things, I'm going to use eraser again and erase number 5. You can look at it on the video later.
Can you give some examples of how carbon is middle too?
Yep. Yeah, they'll come with the later ones. So basically what I'm going to do now is 6. I've got a sequence I like to follow with it. 6 is C8, C2, C2H2. Okay, what would go in the center? C. Okay, 1, 2, 3, 4. You put another C next to it. 1, 2, 3, 4. And you form a bond, right? Now, where are the hydrogens going to go? One on either side. Okay, so you do that. So now you have an electron pair here and here. So what's that going to do? That'll form a bond. This one and this one, what is that going to do? That's going to form a bond. So the structure looks like this. So what is that geometrical structure called? Linear. That's linear also, okay? And another example of this kind, and I'm going to erase part of it. And again, the later slides show what I've been doing all along with my thing, but I'm asking you to kind of ignore my bad handwriting and just rely on the logic. But essentially with this, another example of this would be HCN. Oops, go back. HCN. Okay, what would go in the center with that? The carbon, good. So you have 4 there. Where's the nitrogen going to go? Right next to it. So you put the nitrogen here and you orient it in such a way that you have the holes available. Okay, then you form a bond. Now notice how many open spaces are there? 5, right? So you only have 1 hydrogen. So just put that at the other end and form a bond there. Well, this forms a double bond now. This forms a triple bond. And so now you have the structure that looks like this. Now, what structure is that called geometrically? What structure is that called? Let me make it clear on here. What structure is that one going to be? Linear also, okay? Same as the other one. It just involves that. But nitrogen's more electronegative than the carbon, so that's going to be more polar than the CH2, C2H2 is. Yes. Sorry? Yeah, usually. Yeah. Yes. Particularly between carbons. Yes.
The 2 extra electrons left on the outside of nitrogen, or
That's an electron pair.
do you leave them like one on each side, or do you like
Put them in a pair because they're in a separate orbital and has a specific orbital that we'll talk about in the next chapter. Okay. So now what we're going to do is go to the method that's in the, I'm going to erase all that's on the slide and go to the method that's in the book using numbers and such. You can use my method or you can use theirs. And as Dr. Ott said, they're both, okay? So, yes.
How do you know if, like if it's not linear, then what is it?
Well, we'll get into the other structures like tetrahedral, whatever else in the next chapter. But right now, I just want you to keep it simple. And the only ones I've really taught you are linear and trigonal planar.
So we can expect this linear.
Yeah, if I ask, but I'm not likely to ask that kind of question. But that kind of question is on that worksheet I'm giving you for the weekend, which you can do. The other ones are more complicated, which we'll get to later. Okay.
The other ones wouldn't be on the test?
No, neither would the linear or the other one be on the test. I'm not going to do that because that's more related to the hybrid orbitals and other things that's talked about in the next chapter. Okay. Okay, so now let's go to the slide version, essentially the version that the book uses. And this is more the numbers thing, but I'm going to delete what's on the slide. So first here, you draw the structural showing what atoms are bonded to each other, put the least electronegative element in the center. So essentially here, CH4, there, this with the most things, that goes in the middle. Okay, so that goes in the center. So you count the number of valence electrons around it, but again, it's a kind of thing where sometimes this rule works, other times it doesn't. That's one reason I like my method better. But essentially what they're asking you to do is count the number of valence electrons available. So here, the skeletal structure, you put a C and you have 4 electrons available there. The hydrogen each has 1 electron. And then this one has 1 and you have 4 of them. So there are 4 electrons around each one. So times 4, you subtract 1 for each positive charge, add 1 for each negative. So you have 4 valence electrons here and then 4 valence electrons there for a total of 8. Okay, so basically you get a variety of ones like that. Complete an octet for all atoms except hydrogen. Well, carbon, that's complete the octet. So essentially you have 2 there, 2 there, 2 there, 2 there, and you put the hydrogens there, 2, and they'll just have 2 around it. And so then that's their structure. But I find my method is better, okay? That's why I taught it to you. Many students would find this confusing because it kind of pushes your mind in another direction, okay? Do you see how your mind's going a different direction? You're not really thinking about what it looks like three-dimensionally. You're kind of thinking, oh, counting number of valence electrons. Oh, that's more complicated, okay? But it works anyway. And but unfortunately, the nature of it when you're doing it, it kind of adds a level of complication that's unnecessary. Complete an octet, and then the 4th rule: if the structure contains too many electrons, form double and triple bonds on the central thing as necessary. And if you were to write those as a set of rules and try to work the homework problems without using my rules that I kind of taught you, a lot of students would get lost with this. Okay, but it's useful as an adage because the counting of electrons is important in organic, as you'll see next year. Okay, because basically those are the ones that move along the chain. Those are the ones involved in hybrid orbitals and other things, and involved in chemical reactions, whether it be special kinds of more electronegative ones or electropositive centers, etc. Lewis acids, Lewis bases involve electrons. So there is some value in that, as Dr. Ott said. Okay, so draw the Lewis dot structure of nitrogen fluoride. Let's do it in my method first. What do you put in the middle? Nitrogen. How many does it have around it? 5. Very good. Okay, so we put it in there, put 5 around it. Nitrogen, 1, 2, 3, 4, 5, 3, 4, 5. Correct? How many fluorines do you have? Fluorine looks like this with 7. It essentially has 1 place it can bond like that. So how many do you have? 3. Okay, so then you put the other fluorine here. 7 there. There, you're done, right? See that? Okay, so now let's erase on the slide, and then you'll see what they do with it. Nitrogen is less a negative than F, so put N in the center. Okay. Now this step works with nitrogen less electronegative than this, but what about CH4? Would it work there? With carbon, is carbon less electronegative than hydrogen? No, it isn't. So it breaks the rule with that, okay? So basically, the methane is the first one I've always taught people how to do. And this kind of interferes with it if you're to follow their rules. But with nitrogen, it does work. Yes, Nick, you had a question. The holes, yeah, the most holes. But here they're doing it with their steps. So I'm teaching you their steps too, because it is important to understand sort of both.
Carbon would usually have most, just because it's positive and negative.
Yes, yeah. With the nitrogen, it wants to be -3 nitride, but that's because it's more electronegative. It's on that side. So let's go through their steps. Well, here you put that. Count the number of valence electrons. And you got to draw, you got to put the structure there. So counting them. Okay, how many valence electrons are around it? Counting those valence electrons, how many? No, just count the number of valence electrons. There are 5 for each nitrogen, so there's 5 for the nitrogen. How many valence electrons are around that? For the fluorine, there are 3 of them. So how many would that be? There's 7, so 7 times 3 is 21. Okay, so you got to put up 21, a total of 26 electrons around it, all around it. And those are steps that are sort of extraneous, but it's important to understand. See, you got the 6, 5 with 26 valence electrons. Draw single bonds between the nitrogen and complete the octet on the nitrogen there. So they say draw single bonds. So that uses up 6 of them, right?
Yeah.
Okay. And then you draw in the complete the octet on the rest, and that uses the rest of them. So essentially you have now 26. Now you have to put 20 around it. So the 20 get put around it like that. And then essentially you are done. So essentially you now have all those together and check the number of electrons around it. Are they equal? Is 26 equal to 26? And the answer would be yes. And that says you're done. And that's a total different way of thinking. But that way of thinking, particularly for biology students, gets them lost, okay? Because it more involves numbers than the concept or the picture things, okay? So there's value for both, okay?
That molecule will be polar or no, since they're closer together on the electricity.
Well, is it gonna be polar? Think, this is like a pair that goes up like that. Is that gonna be polar? Yes, because the vectors all point out at the fluorine, but also there's a little vector here, so the vectors are uneven, so that's polar, because you got this electron pair up there, which is different. But if you had CF4, would that be polar? No, because the vectors there would all cancel out. So the vectors all point out at the fluorine, because that's more electronegative, okay? So when they cancel out, and then it's not considered nonpolar. Okay? And let me erase what's on the slide again. Okay, now draw the Lewis dot structure for carbonate. Let's do it with mine first, my method first. What goes in the center, folks? Carbon, you put 4 around it. 1, 2, 3, 4. Put an oxygen next to it, like this. Put another oxygen over here. and another oxygen down here. Okay, so you have now all those oxygens around it. Okay, how many extra electrons do you have? Because it's -2. How many extra electrons do you have? What? No, I'm saying in this thing that's on the structure, how many extra electrons do you have? I just circled it. How many extra electrons are there? 2. You've added 2 electrons to it. So basically you'd put 2 electrons around this and around that on those 2. Now, what do you notice that's missing now? You have an electron up here and one there. So what's going to happen? What's going to happen to this electron here and this one there? That'll form a bond. So you get a structure that looks like this. Okay, with a minus here and a minus here, and then this has there associated with that, and that's the structure. So that essentially is the structure for carbonate. Now, what structure would that be? Yeah, the trigonal planar, because it's flat because of this double bond and such, but the whole thing is -2 because this, and also it has what's called a resonance forms, but we've run out of time, so we're not going to get to the resonance forms part. So basically that tells me the test will be delayed 1 day until Wednesday, not Monday. Yes. Huh? Sorry? Yeah, well, not really, because with the resonance forms, the double bond, say the double bond could be here, and I might as well teach that to you briefly, like that with the different charges, or it could be here, down here, like this, and it shifts around it. So it's one whole thing, so they all eventually cancel out. The other one would be like this, and so that's a resonance form also, and so basically they all 3 have together, and that's what's called a resonance form. So basically the resonance form, when they have resonance forms like that, it would be considered nonpolar for that ion because it all cancels out.
Dr. Douglas,
Yes.
but I'm kind of confused in the carbonate.
Okay. But what's the confusion?
So you're just like adding 2 electrons just to
Yeah,
whatever.
because the carbonate is -2, right? So how do you get a -2 charge? You get 2 extra electrons, right? That's where the extra electrons came in. I put them in here. So essentially one go in there, -1, the other one went in there, -1. So now you have this extra electron and this extra electron, so that forms a double bond. And when you have charged species, you add an electron to it. And if you want more help with understanding that part, I can help you in my office or later, whoever wants to it. But essentially, we've reached the end. So I have one more lecture I want to do regarding resonance structures, formal charge and such, so we're not quite done the chapter. But I'll do that on Monday, and so our exam will be Wednesday or the week after, okay? And we'll have a little bit more overlap. Any questions?
Experiment 13 Monday, right?
Yeah, and that'll give you practice for the basic stuff, okay? And you could read ahead and put in that stuff too, because that'll teach you a little bit, but I want to cover that in class too. So that's why it's better to have it as a worksheet. Any questions? Those of you virtual, any questions of you? We're done for today. Okay, thank you very much. Have a good day, everybody. I'm going to stop the share now.